Hi everyone, and welcome to another video of CS202 Online. Today we're going to continue talking about dynamic memory allocation, but whereas last time I introduced the concepts of allocating memory and deallocating memory and the risks such as memory leaks and dangling pointers, today's job is going to be to take that knowledge and actually start coding with it. I also want to show you a tool known as Valgrind that allows you to detect memory leaks and helps you trying to fix them, actually, because it kind of tells you where they're at a little bit and tells you if there's memory leaks. Now, the tool is not perfect, but it's definitely something to use and take advantage of. And in addition to that, I want to just code like all class for the most part. I just want to spend it all coding and also code two-dimensional and three-dimensional dynamically allocated arrays. We've seen how to make one-dimensional arrays, and it's just change of the syntax. But when it comes to two-dimensional and three-dimensional, it's a little tricky, so you'll get to see how that's done. After that, I want to introduce the concept of shallow versus deep copy, which affects how dynamic arrays are copied when you do an assignment in C++. And finally, if we have time, I would like to revisit classes and update what we can do in our constructors and destructors when it comes to dynamic memory allocation. When I first talked about destructors in quite a few lectures back now, look how far we come. I said that they weren't really useful at this point until we talked about memory. Well, now we have, and now we're gonna come back and I'm gonna show you what kind of things you do in destructors, which hint, that's where you typically do your deallocation of any dynamic variables in your class, and the constructors is where you do the allocation. So yeah, full circle when we come back to that. And so that'll wrap it up, assuming that we get through all of this actually in one video. But we'll see how long it goes. Okay, so let's go at it. Let's just start coding. So I have here a simple program, and it's gonna become far more complex in a little bit here. But I wanted to just start out with the basics. I have an integer variable. It's a static variable in comparison to a dynamic variable. Again, this is when I say static, I'm not talking about building something like this. That's a different kind of meaning of the word static. Okay, and I want to just show you the address of operator. So if you run this program, you see that we get an address, and this address is in hexadecimal. Let's run it again. Look at the address now. And it's in DB84. I forgot to see what it was before, so I'm going to run it one more time. And you can see that it's giving us the same address, right? So you might be compelled to say, that address is always going to be that address. No, it's not. This is just the debugger that is kind of probably using special addressing to make the debugger work better. But you have no control of this address. So as my second experiment, I'm going to go ahead and do this in like the compiler here. So I'm going to go ahead and run the program. And you can see that already we get a different address than we were getting here, right? So here I'm getting address ending in 84 or 84 because it's hex. Technically it's not 84. And here we're getting D4, okay? So already there you can see that the addresses are not the same. But if I run it again, you can see that I'm already getting different addresses. In fact, look, every time I run it, I get a different address. And this is a static variable, so it's not even dynamic. But even static variables, you don't decide where they go because you don't decide where your program runs, like what part of memory you get. So memory is divided into a stack and a heap, and we'll talk about stacks later on in the semester. But ultimately, static variables that are like these are kept in the stack, and dynamic variables are kept in the heap, and they grow onto each other, so there's flexibility. All you need to know about that right now is that you don't decide where they go there. The operating system does. And that's why we're getting different addresses there. Okay? So already there, you kind of get to see that, you don't know where you're going to get. So let's move on to dynamic variable. So for a dynamic variable, I want to go ahead and actually, let's just make a pointer first. Yeah, let's make a pointer first. So let's make a pointer called P. Let's go ahead and assign the address of X into P. We know what the address is because we're counting it. So just right beneath it, I'm going to say P gets the address of X, and now I'm going to say cout P. And if my calculations are correct, we should be getting a 22 printed, regardless of what the address is. So you can see that we are getting a 22. And now here again, in visual code, like it's giving me the same address every time. And it's a weird address because you can see it's almost like at the end of the numerical representation there because of those. But don't trust it. Again, it's not going to be the same anytime. If I run it here, I'm getting different addresses every single time. Pretty different addresses, okay? But I'm still getting 22. That's consistent because that's what I'm getting. Okay, so pointers work. We're able to store addresses. Very cool. Can I see out P itself? I can. I just have to remove the asterisk. That's going to get not the value that the address is pointing to, but the actual address itself. You can see that both cout in the address of X and cout in P give us the same values back because they're both basically pointing to wherever X lives. Cool. All right. Moving on, let's go ahead and dynamically allocate a variable instead of doing it static like this. So let us go ahead and say P gets new integer. And then let's just go ahead and see out whatever that integer is. Like, let's just see what's in there as we get it. Because I mean, that's the other thing. When you, just like any variable, whether it's static or dynamic, when you get this variable, you don't know what the contents are. You don't know what was there. There's probably something that was there. In fact, the way memory works, you will learn, like, it's just, there's stuff in there. Like, there's gonna be some leftovers. You just no clue what they are. It's completely RNG in it. Well, not completely, because if it was truly RNG, then you could use that as an RNG generator or something. But yeah, so you want to start by cleaning up whatever's there. Okay, so let's go ahead and clean it up or assign something to it. So let's go ahead and put like a 25 in there. And then let's go ahead and see out it again and see if we actually get a 25 out of that. And let's see out the address because I'm curious where P is. In fact, I'm also going to see out the address of P before I allocate it. So, because again, that should be some random value. Because again, it's just a variable of an address, but who knows what's in there. So let's just run it all here, and then we can run it in terminal. So here, I think this just gave me a blank, or is that just a 0? No, this 0 is probably, well, there's 4. No, this 0 is connected to this line. So the debugger is being nice. It's initializing my pointer to 0. Again, I may be misled to think that this is always the case. It's not. It could have garbage in it. It's undefined behavior. You should initialize it yourself. How would you do that? You do that, and then for sure you guarantee it's safe. But we're not going to do it just yet because I want to see what the terminal gives me. And then I am allocating it, and then I'm printing out the contents of what I just allocated. Again, debugger is being really nice to me today. Debugger is giving me an integer, dynamic variable integer, and it's pre-setting it to 0. That again is not the case always. You can't trust that to be the case. So beware when you're coding. You think these things are happening, and then you don't know. And when you run it in CodeGrid, it doesn't do these things. CodeGrid is more like terminal. You're wondering why it works in your computer, but not on CodeGrid or anywhere you're testing. So you should be responsible for your own initializations. No one else but you. All right, we assigned 25 to it. We print it out. It does contain 25. And if we take a look at that address, we can see that it's a completely different address. So probably assigned because this is in the heap instead of the stack. But again, terminal time, because I like the terminal better. I trust it more to be more realistic of what we will see in like actual real world situations here. So we run it a few times, and what we get is, oh, well, look. The terminal this time is kind of not being, not being as reliable as I thought to give us true RNG, because it's actually giving us the exact same memory each time. Wow. Okay. All right. Okay, terminal. I'm gonna play that way. You can. Okay, there we go. We waited a little bit longer. I ran it again. I recompiled and ran it, and this time at least it gave me a different address for the pointer. You might be asking yourself why. Oh, look, this time it was just a matter of waiting and not run. So if I run really fast, no, this time, now I'm getting different addresses. Was I getting them before I didn't notice that? Oh, I was. It's just, it looked the same, but they're not. Yeah, and I was never getting the same address. They they just ended in Z0, but like the addresses were different. Okay. The address is different of the pointer, but it's still initializing it to 0 without me doing that. That is really not the case always. Like, I wish it would have not done that to me, but it did. But just take my word for it, I guess now. That will never always be the case, okay? Like, there will be some instances where allocating with new will not, I mean, just as common sense, which is a dangerous term to use, especially with programming, this is a variable. And like any variable, it's not initialized for you. So it could contain anything in it, whether it's an integer or a pointer or anything. So that's a red flag right there. New also is not part of the C++ rulebook that it will set whatever you do with new to 0. Unfortunately, it just happened to do it here, but trust me, it is not. Okay? It is not always the case. Bad thing, okay? So, oh well. Anyways, all right. So what I have here is a working program, but I am not deallocating, right? So now is the time to show you Valgrind. Let's show you. Actually, maybe Valgrind will be my save. It will rescue me, and it'll actually give me truly randomness. We'll see. Maybe it won't. We'll see. How do you run Valgrind? You run Valgrind in Linux by going ahead and writing the word Valgrind and then passing in your executable file, which in my case is a.out, or it's /a.out. Yeah. Okay. Press enter and then look at that magic happen. So, ooh, I like it because it gave me a bunch of errors. So when you do that, you'll say, by the way, if you see Valgrind is not installed, then you can install it by doing sudo apt-get install probably Valgrind, and then it's going to ask you for the password, but then it'll work. Okay. So yeah, I have it installed already, so it's no problem. But yeah, or just Google how to install Valgrind and see like a billion different responses. So really, there's no reason why you can't figure that out. But yeah, so you can see memory check, blah, 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 using Valgrind. It has a rule set, so you can do -8 for help and information about other stuff like copyright, I guess. And from there, you are going to see a bunch of either, well, hopefully you won't see errors because your program is fine. In my case, I do see a huge, ridiculous amount of errors because there's a memory leak. And probably it doesn't like the fact that I am using uninitialized information. In addition to that, you are going to see what the output of the program is. If errors show up as the program is progressing, because again, with dynamic memory allocation, you're making memory at runtime. You're allocating memory at runtime. So like, within your program, there might be a point where you run into an error. That's when the error will pop up here. So you may see the error mixed within the output. In fact, somewhere in here, there should be the first 0. Here we go. So from here on out is errors that happen between this lines number 6 and lines number 8 were all those errors. And then from this line on, there were no additional errors created. Although you will see down here at the end what is known as a heap summary. So this is where your dynamic memory allocation lives in the heap. And you can see it says in use at exit is 4 bytes in 1 block. There are 3 allocations and 2 frees. I know that doesn't look like that to be the case, but it's happening. But what you really want to check and see and worry is the leak summary. This is your memory leak summary. There's different categories. You should not have anything on these. But like, I guess you can talk about it from like worst to not so worst down here. This being the worst, it says you definitely lost 4 bytes in 1 block, meaning that there was 1 variable in there, 1 block. If it was an array, each member of the array could be a block. So it says 4 bytes in 1 block means you lost 1 variable with 4 bytes in it. Sounds like an end to me. That you never deallocated. And so when the program ended, sure, it returned to the OS, but you hadn't released something. So that means you kind of lost it. So that's what it shows, okay? And then it shows you the error summary list, which is what it's above it. So that's more errors than I thought I was going to get, actually. But that's good. That's good. So let's read the errors, actually. Like, read the errors. Like, okay, people sometimes will say oh, I need help with this, and they post the error and the error literally says how to fix it and where the problem is. I'm like, did you actually read the error? It tells you how to fix it. Just read it. You know, like errors are not all, we're all just used to like an error being like a foreign language. You know, it's not. Sometimes it is, don't get me wrong. But a lot of the times these errors are actually like pretty clear about how to fix them, particularly compilation errors. Valgrind so, but compilation errors, they're actually pretty darn good these days. Okay, so reading it, it says use of uninitialized value of size 8, probably because pointer P is in my system using 8 bytes for an address, because it's a 64-bit system more than likely. It's a VM, but it's probably a 64-bit VM system. And it tells me the memory location, which that doesn't really help a lot. And there's a question mark here. I think if I rerun this with the -G flag, it might get better results. Oh, no, 0-G. I believe the -G keeps some extra information when you compile your program for a debugger or Valgrind to feed off of. So if I compile and then run Valgrind, I should get better errors. We'll see. Yep. So you can see here. Oh wait, no. At least that one's the same. But sometimes it gives you better intel. So try it if it works sometime. So OS stream buff iterator card tray blah 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 blah. Here's a line. Main 6. So you can see that error is coming from line 6. Conditional jump or move depends on uninitialized value. That's already your first red flag that you did not initialize something. So that's definitely an issue. So while I am getting a 0 with Valgrind, so Valgrind's still being cool about it, there's still a problem there that you should fix. Okay, so there's the first error. Still talking about line 6 there. Still talking about line 6. You might get the same error multiple times because it's really trying to be descriptive. Conditional jump move or depends on initialized value. Again, the same thing. But now we get line 8. This one is because in line 7 we allocated an integer, and again we are printing the contents, which we just got lucky and got a 0, but again it's uninitialized, so it's who knows what we're going to get. So these are actually legitimate errors in our program. They're not memory leaks or dangling pointers, they're just simply errors because you're not initializing things. So Valgrind is cool about that, helping you find those kind of issues. While you're safe in this one because it's both zeros, those numbers could be any value. They literally could be anything. We don't know for sure. And just because you ran it once doesn't mean tomorrow it's not going to be right. It's undefined behavior. Okay, so let's go ahead and fix a couple of these. So first thing, set that to null. So now that should get rid of this error. This should just print out a 0, but this time we know it should be a 0. Here, this is just bad in general because we shouldn't be printing that uninitialized thing. So we just don't want to have this line at all. And then we were going to leave the memory leak, but at least that will get rid of the errors. Okay, so we run it again. We should get 0 this time here, but this time it's guaranteed to be 0 because we set it to be 0. If I run Valgrind, I think that'll get rid of all the errors except for the memory leak. Yeah, so you can see we have 0 errors this time. So don't just assume because you got 0 errors, you just pass all the Valgrind checks. No. It's a good thing though, you're getting there. But as you can see, this looks more clean. Here's our output, which matches what this gave me, except for the address being different. And in the heap summary, you can see there's still definitely lost 4 bytes in one block. So we do have a memory leak in our program. And of course, that's because we never called the allocate. So let's go ahead and call delete p, and that should fix our memory leak. So as you can see, the output of Valgrind is getting shorter and shorter. That's a good sign. You can see that we don't have any of the leak summary section. It just completely skips that and says all heap blocks were freed. No leaks are possible. Those are some bold words to have, because I don't know. if that is guaranteed. I feel like, well, Valgrind might be really amazing. I wouldn't 100% rely on it and say like, oh, okay, Valgrind says it's safe and it's 100% safe. But it definitely is safer than you and I can probably like by hand figure out. So we'll call it we'll call that good enough for us. And you can see in use at exit is 0 bytes and 0 blocks, whereas before it said 4 bytes and 1 block. The total heap usage says 3 allocations and 3 frees. That's a nice thing because it matches, it looks nice, but not necessarily have to match. You'll see sometimes they don't match when you're doing arrays and things. And 73 bytes allocated. That is, don't worry about that. That's just internal. Don't worry, just let it be. Okay? But yeah, so we're good. Their program is safe and we can submit it. So this is what you want to get from Valgrind, something like this. Okay? No errors and no leaks allowed anymore. And this is forever. Like this is literally gonna go into 302 and so on. At this point, we just expect you to always not have memory leaks, unless mentioned otherwise, and no errors. Okay? Let's introduce an error, but not a memory leak. So let's move the delete. Here, there's no problem because this is a dangling pointer, but not necessarily an error. So I don't think that this will give us any errors because we're just printing out the address that remains. Yep, no errors there. The error would be here because this is a real dangling pointer that's problematic. Because if we deallocate P, but then we try to print out the contents of it, we're dereferencing a pointer that was already that was deallocated, like whatever it's pointing to. So what we're dereferencing no longer belongs to us. That should give us an error in Valgrind, but it doesn't. See that? So you can't 100% trust Valgrind to be safe. Because technically speaking, oh wait. I forgot to save, so hold on. Let's not talk smack about Valgrind just yet. I mean, you can because you can't trust it all the time, but still, I would hope it detect that. Yeah, there we go. So it did actually detect this error. So you can't trust it all the time. That still stands, but it should at least detect something as trivial as this, which it did now. So you can see this kind of error is the kind of error you're going to get from a dangling pointer. Invalid read of size 4. Address that is 0 bytes inside a block of size 4 that was freed. See, so this is a sign that you are accessing something that was already freed, or in other words, deallocated. Okay, and it tells you where it was allocated and where it was deallocated here, and so it still says that there are no memory leaks, nothing in use, and everything is good except it says 1 error. Okay, so that's what it looks like when you have a dangling pointer issue. And not just a dangling pointer, because I mean, technically, how I had it before, like this is a dangling pointer, but not necessarily a problematic one, because you're not accessing the dangling pointer and it's not giving any errors. So it's only going to give you an error if you're actually messing with a pointer that's dangling. Again, the solution to this is, of course, to set it to null. And then you would be good to go. Okay? So that's Valgrind 101 for you. That's how you use it, and that's how you take advantage of it. And great power comes with great responsibility, blah, 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 blah. Okay? Moving on. Let's go ahead and save this as number 5. Remember, these are available for you to download so that you can play with them. Okay? Of course, you can just copy them, but I try to make it easy so you don't have to spend time copy pasting, or I mean, like hand copying from a video. You could use OCR though, that'd be cool, but it's kind of overkill. Okay, so next I am going to, so you've seen how to allocate. Let's just really fast. Let's do an example with an array. So let's just make an array of size 10. Let's make one that's actually needs to be dynamic. So like int x, and then we're gonna read in from the user that value of x, and then we're gonna make the array of size based on x. And then forgot about the one new. Then we're going to deallocate it, so you can see that the allocation happening. And maybe before it, we go in and we modify some spot in it. So like maybe like spot 2 gets 11. C out P2. Okay, so that's good enough for now. Let's just go ahead and run it. And you'll see that it's going to ask me for, well, not ask me because I forgot to word prompt. Put a 5 in there and press enter. You can see that we are getting the 11 out of this. In fact, let's run it in Valgrind. So in Valgrind, if there's interactive IPO, it'll just stop like that. So then you can go in and put in the 5. You run it, everything is fine. No memory leaks because we have the delete. If we come in after delete, you'll see that we have 20 bytes in one block. So in this case, it's not, even though it's an array, it's not splitting it into blocks. It's still considering the array to be one block, but the math makes sense because you have each integer is 4 bytes and you have 5 of them that were lost. So you have 4 times 5 is 20. So yeah, sometimes gotta do some math here. If I do the same program again, but this time I'll do 10, you'll see 40 bytes because it's again 4 bytes times 10. If I do 1 byte, then I am going to have 1 byte memory loss, but I'm also not going to have some errors, and those are because I am out of bounds, right? So the array is only size 1, but I am accessing the third element of the array, and so that is an invalid write for the 11 assignment and invalid read for the cout statement. So Valgrind is your friend. It actually helps you fix problems in your code that will otherwise go unnoticed, because I mean the code compiled without any errors. There's probably some pedantic flag or W wall or whatever that will probably give you a warning for that if you put it. But you know, this is one extra safety thing you can check. And trust me, this is one extra safety thing that that we are going to be testing for when we grade your programs. So be aware of that. Be aware of that. In fact, I'm thinking for a second, yeah, I gotta make sure that I test for Valgrind on one of the assignments. Okay, anyways, all right, so that's, you know, memory leaks for you. Let's see what the error looks like when you try to delete something that was already deleted. Yeah, so let's call delete twice. Or simply, actually, here, we can try something. Let's make an array of size 0, okay? So I'm gonna run this again. You know, with a big number, it works fine, no bugs. But I'm gonna run it, put 0. So the delete's okay. Okay, the delete's okay. It just assumes that even though it's an array of size 0, it doesn't give me an error. Okay, yeah. All right, that's not what I thought would happen, but fine, fair enough. All right, let's put a second delete then to really introduce problems. Okay, so here we get a different kind of error that says invalid free delete square. So it's like there is some issue with your code. I don't know if you're deallocating a single variable or an array of them, but something's wrong. And it'll tell you the line, as you can see here, lines 9 and 10. And then, well, particularly it says 10. It tells you, well, let's read it closely. It says invalid free or delete by main line 10. So the problem is line 10. Then it tells you the address is 0 bytes, which means it was already allocated, inside a block of size 220 that was freed by another delete operator that is found at line 9. So basically, this is pretty nice about telling me like, hey, the stuff you're deleting in line 10, you already deleted in line 9. So you might want to check up on that. So this is really, really nice and descriptive. You just got to skip some of the weird things like USR lib. Just ignore this stuff. So you have to kind of remove the randomness and read the real error because it's really useful, okay? And it also tells you where you allocated it in case you want to know. So like, hey, by the way, this was allocated in line 6. So line 6 allocated it, line 10 or line 9 deallocated it, and line 10 is the problematic one because it was already allocated. So it tells you everything you need to know to fix that. It tells you where the error is, where you initially deallocated it correctly, and then where it was all initialized from, just in case you want to track the history of the variable. That's all you need. Like, come on. Like, it's literally telling you what to do. So, you know, just read it and believe it and, you know, embrace the meta of actually using Valgrind to fix problems in your code. Don't, like, I'm not emphasizing this because I'm mad, but I'm emphasizing this because, like, you know, if somebody is putting you all these tools to fix your problems quickly, why suffer at just like, oh, my code doesn't work, let me just stare at the code for 2 hours and hope that like divine illumination highlights the line that's wrong. That's not going to happen, more than likely. And you could fix your problem in 5 seconds if you actually read some of these tools. So like, believe in the tools and start using them. You'll grow as a programmer. You'll become more efficient. Your life will just become better. Errors will no longer be something that you fear. They'll just be part of the process because you know how to quickly fix them. Okay? So please, please, please do that for all your programming. And stop using Notepad. Use an actual IDE that does things like syntax highlighting. Because I know some of you are using like Notepad. And shake my head. Okay. All right. So okay. So now I think we saw enough Valgrind. Play around with some errors that you know what's going to happen, so you can see what the errors look like, so you can learn from them and then detect them quickly. Okay. For now, I want to move on to actually multidimensional arrays. Okay. So how do I make a two-dimensional array in C++ that's dynamic? I know that if it was like a normal array, like a static array, you know, I can do something like this, and then I can access it like this, and like this will compile and run, no problems whatsoever. And it's nice because like you know the rows, the width, and whatnot, and you can go as many dimensions as you want with this stuff. You know, like that. And so you just gotta keep track of it on hand, on paper. Oh wait, I put 1, 2 in brackets there, I guess. There we go. And you're good. Like this stuff is beautiful. It's really nice. But unfortunately, that is not how you do it dynamically. Because dynamically, you only have one level of dynamic allocation that you can do. So if you want to make an array, and we're gonna stick to integers for now. You can do something like this, and then give it a size. And then if you want to make a two-dimensional one, you can't just go in and do something like this. What you need to do is you need to make an array of pointers and then have those pointers point to other one-dimensional arrays of whatever you want if it's a two-dimensional one. So let's switch for a little bit to the iPad and show you some pictures that I prepared for that. Okay? So normally when you're making your arrays, if you're making a two-dimensional array, you think of it like a square with rows and columns, right? Like a little table, basically. I want you to take that one dimension down into a single dimension and tell me how you would represent it. If I told you take a two-dimensional array and represent it as a one dimension, so maybe like, let's do a simple one. So let's do a 3x4, okay? And I say, convert this into one dimension. Bring that down a dimension. Well, you can just take every single row and make it its own array. And then put those together to build the same array. Right? And because it's one dimension, then you can just basically put them one after the other like this. But that doesn't matter how you think about it, like visually. It's separated into that. Okay? Now, what if I say, okay, do the same thing with a three-dimensional one. So now we're going to do the same array. But now we're going to add a depth to it to represent the third dimension. And maybe just a 2. So basically now we have a 3x4x2. What if I say bring that down one dimension? Well, all you got to do is just draw two squares, right? So that's the first layer. This is like the second layer. You can think of it like layers, right? And if I say bring those down like another dimension, then you're just going to make two of the top ones. So the first layer is split into that, and the second layer is split into that. But ultimately, it's all just one big continuous thing, and you can use math to jump back and forth and whatnot. And that's how they did in the CDAs too. So you can bring things down a dimension. And you can go further, by the way. You can go into 4 dimensions. Like, in fact, I don't want to draw like a hypercube in here. So if I wanted to tell you, hey, I want a 3 by 4 by 2 by 2 like hypercube, 3 by 4 by 2 by 2, then I would probably just actually do the breakdown version first. I'll be like, okay, you know, I'm gonna say the 4th dimension is time, and there's 3 time periods. There's T1, T2, T3. So I'm gonna do it like this because unfortunately I'm really bad at drawing 3-dimensional, 4-dimensional figures. I don't know about you. So I'll probably just do this, okay? I can draw a hypercube technically. It looks weird, but you know, you just put a cube like that. And then I think you gotta connect the corners. So you do like this corner here, this corner here, this corner here, this corner here, this corner there, and then you have like the hidden corners, which go here. So like, you know, this hidden corner here would go here, this here, and this here, and that would be like a hypercube, a 4-dimensional one at least, tetracube or whatever it's called. So yeah, but anyways, the point is that's what you do. You break it down, right? So that's kind of what we're going to be doing. But then you might ask yourself, okay, can I just break it down into these thingies and call it a day? Well, no, because you need to keep them organized. So you need an array to keep the subarrays organized. And it turns out that that array, and also we need to allocate those subarrays. Because again, we need to allocate every single one of these 1-dimensional arrays. We need to call new operator on. We can say like new int 3. Right? So we're going to need to do that like a lot of times and keep it all organized. How do we know which one goes after the other ones? Like, how do we actually organize that? We either do it the C way, we just make some massive 1-dimensional array of the right size and then use math to like traverse it, which is a pain and you don't want to do that. Or we can make arrays of pointers to do that. So what do I mean by arrays of pointers? Okay, going back to the simple example with the 2 dimensions. What I'm going to do is, instead of breaking this down into just 4 arrays, I'm going to actually have a 5th array here. This is going to be sort of like my organization or like logistics array. It's going to be the same number as the number of rows, but this is not an ordinary array. So like this could be an array of numbers. So like I could have a bunch of numbers here. This is actually going to be an array of pointers. And these pointers are going to be pointing to the beginning of each of the real arrays. And by real, I mean like they actually contain data, not pointers. So now I have a pointer, call it like the main pointer, single pointer that's going to point to the beginning of this array, because I know that's what actually happens, right? When I say something like int p gets new int 5, what I'm saying is in memory I have p, and then I have the block of memory for the array, and p points to the beginning of that. Okay, so really what I have visually is pointer p pointing to the beginning of an array, and by beginning I mean it literally points to the first element of it. Okay, so now that's what I'm going to do. I'm going to have p point to some dynamically allocated array of pointers, and each of those pointers will point to the beginning of the dynamically allocated array of actual data, of integers or characters or whatever it is. So this is an array of pointers, or pointer array, and then these 4 are actually array of whatever the data is. So I guess integers if I'm doing integers, okay? And then this is a single pointer too. This is just a single pointer, but it's not any kind of pointer. It's actually going to be what I'm going to call double pointer. Okay? So that's trippy. It's a little trippy. But why do I put double pointer? Because what if I want to access like the 2 there? Let's put some more numbers in here. 4, 5, 6, or whatever. 4, 5, 6, and so on. Maybe like an 8 there. What if I want to access the 2? Well, to access the 2, I got to go to 2 pointers, technically. I got to go 1 pointer here, and then a second pointer there, right? So I got to do 2D referencing. So basically, I got to go, it's like a scavenger hunt. Like, I say, okay, I start at beginning, and I say, I need to go to the address of the first location of the pointer array. So I go to that address. So that's 1D referencing. So going to that address. So like basically from here, from here to here, it's 1 address. Then from here, I gotta dereference this address again to go to here. And this is what the real data is at. So I gotta do 2 jumps. So that's why there's 2 asterisks. Although better way of drawing this is to draw a single asterisk here, but just know that it represents 2 to get to the data. Okay? So that's it. That's how you represent it. Another way of drawing this is the one that I had pre-drawn. So I'm gonna copy and paste it over. Is this one. So here we have an array of size 4, but this is me declaring the pointer array in it. Okay? So for me to declare this pointer array right here, what I'm doing is I'm not making any kind of array. I'm making an integer array. How do I know it's an integer array? Sorry, a pointer array, integer pointer array, because this is integer pointer here. Unlike this, which is a normal array. Okay, that's like a normal integer array, and this is an integer pointer array. That's a data type right there. Okay, so with this said, I am going to go ahead and allocate this array here. And then to allocate the subarrays, then I'm just going to use the other syntax, which is new. And then these are size 3, so I put that. And I'm going to store this in each of these. I'm going to make multiple calls 4 times to that call to build it. Okay, so to build this array, I'm going to have 5. This specific array, I'm technically going to have 5 calls to new. One of them is for the pointer array, and then 4 more are for the actual arrays that contain the integers. Of course, what if the array is a different size? Then it's going to be based on how many rows I have here. So I'm going to make this be sort of portable to any size array, I'm going to make it a loop, so that it loops through each of these and allocates them. Okay, so let's do that first, and then let's go ahead and build up to the 3 dimensions. Okay, which will be the same concept, just extended another layer. So I'm going to put it like that. So I'm going to keep it like this here, so we can see it. Okay. So let's go ahead and start by making this pointer. So I'm going to make the pointer array of size 4. So I'm going to change this to have an asterisk. And so now what I've made is I've made an array that has 4 slots. And those slots are all pointers, integer pointers. And that's it. Uninitialized right now. Now I'm going to bring in the handy dandy for loop that is going to run that size. So here, in fact, to make it more portable code, I'm just going to call int size, and then I'm going to set it to 4. So that way here, I'm going to put size. Okay. So now I'm going to run it from int I equals to 0. I is less than size, so it runs in the same number of pointers that we have. I plus plus. And in here, I'm going to go ahead and say, okay, I would like for each of these pointers that are contained within R sub I, because I'm going to access each of the entries of the array I just made up here, I'm going to access down here, right? So I'm going to go through each of those, and I'm going to call new on those and make the internal array, which is of size 3. So I guess we'll do another variable for that one. So we'll call this like size 1 and size 2 for like second dimension, I guess. Okay, so we'll call this size 2. I don't know why I'm getting all these underlines. Something I forgot somewhere. I should have size 1. Now let's call size 1. So let me fix that. Okay, compile again. Okay. Okay. This is an array of pointers. Because it's an array of pointers, it's not enough to have that single pointer, right? I need 2 pointers because I'm going 2 layers deep, 2 dimensions deep. So I need to make this a double pointer so that it holds. See, a single pointer can hold an array that's just of normal variables. A double pointer can hold an array of pointer variables. A triple pointer can hold basically a 2-dimensional array of pointers. You gotta go 1 pointer up at a time. This is where things get a little weird with pointers, okay? So yeah, and then put that there, and we should be good to go now. Okay? So just to prove to you that it works, let me just write another for loop that's going to iterate through our array and print it out. Okay, so I am going to put for j is equal to 0, j is less than size 2, j plus plus, and then I just need to say something along the lines of cout ari and arj. Am I getting the dimensions right? Yeah, I'm getting the dimensions right. I mean, I want to make sure I don't flip him, you know, the rows and the columns. Otherwise, I could get a sec fault because I go out of bounds. And then maybe we'll add a line feed between each row so it looks nicer. And then we also want to add a space between them. It's going to be full of random zeros or something. In fact, we can fill the data with some random data in a second here. Yeah, I'll do that. Come on, let me get in there. Int j is equal to 0. Put it there. And then put a line feed after this. I'll do it in the same line, just save some space. Because I would want to run this twice actually. I could do it in the same line here, but it's like I want to show you that I'm not cheating on this. So I'm going to run this twice. The first time, I'm just going to fill it with random numbers, just so that it looks prettier than an array with just zeros in it. So I'm going to go ahead and say gets rand mod. Let's do like 9, or well, we can do 10, just so it's nicely formatted, and then I could. Yeah, okay, I'm happy with this. It's just it's rand 0. It's just we get the same random each time. Okay. All right, I think I'm happy with this. So now if we run this, we should get this little 2-dimensional array down here. If I run it again, 3, 6, 7, I'm gonna get the same numbers because I'm using 0. If I did time null, then I would get based on time, so this would actually get different each time. So I get 5 and 7, and if I wait like a second, then I get different. So I'll leave it with well, yeah, let's leave it with random numbers actually. That's fine. Okay, so again, all I'm doing here is just a loop to assign a 2-dimensional array. This is nothing new. It's literally just, this would be the exact same whether it was dynamic or not. As would be me printing it out. Nothing fancy happening in either of these 2 lines that you don't know already. In fact, this should just prove to you that whether it's a dynamic array or not, you handle it the same way with your indexing. The only difference is for creating it, the array, or deallocating it, that you have to use new versus like the nice square brackets. So again, you have 2 new calls. You have one at this level to create the array pointer. So this is the pointer array. So what I'm doing with this call is I am building this right here. And then the other one, this new call here, what I'm doing is these. Okay? So that's how you do that. All right, moving on. Let's go 3 dimensions. So for the 3 dimensions, I'm just gonna copy and paste the drawing that I have. So remember what we're trying to do is we need to go from the cube to the single row. So we have to go through layers of that. So what that really means is that we are going to have 2 layers of pointer arrays. Okay? Actually, yeah, let's try to draw it really fast. See how it works out. Then maybe I'll copy and paste a nicer one I have. So like in this case, If I want to make it a 3 by 4 by 3, so 3 by 4 by 3, and I choose those numbers because that's the drawing I have, so just in case the drawing fails, I can bring in my drawing. So I want to make the cube, right? So, okay, I'm not doing the cube. Screw the cube. Let me bring in my cube that I drew already. It's not even that pretty of a cube, but at least it looks like a cube. It ain't much, but it's honest work. All right, so I want to make this. So the way I'm going to make this is I'm going to split it. I'm going to start out, well, actually, you have a choice to figure out which dimensions you want to do. But I'm going to start with the third dimension, then the second and the first. So the third is going to be like the depth. Let me say this is the third dimension. The second dimension is going to be this height. And then the first dimension is going to be this one, okay? So it all starts out with a single pointer, which it's going to be my R pointer. And from there, I'm going to make a simple array to take the 3 layers. So the third dimension. So I'm going to make an array of 3 things. Okay, and of course the array is going to point to the first one of them. So that one is going to, oh, sorry, blood sugar went down. All right, I'm okay, I think. If I pass out during the recording, that'll be weird. All right, so yeah, so we got, I should like run and get some sugar or something. I'll keep going. Okay, so, whoa, all right. So I got my array, and I got the 3 pointers, which are going to represent my different time steps per se. If you thought of the 4 dimension or the different layers of this cake. And so now each of these, I'm going to do another new call to make an array of pointers of size 4. Why 4? Because we have 4 in this layer too. So you see 4 rows per layer. And of course, the pointer, the line itself is going to point to the first entry of that because that's how pointers work. Hang on, trying to do it good. Okay, and I'm going to do this 3 times because I'm going to do that for that one and then for this one, but I won't draw that. I'll bring that in as I said. And then for each of these, I'm going to do another new call. So let's just pick this one. And it's going to contain the first dimension, which is 3 numbers. And those are actually going to be numbers. So this is not going to be like the int pointer. It's just going to be a single one. So at this layer, it's int pointer. But at this layer, it's going to be 2 pointers. And at this layer, there's going to be 3 pointers now. Okay? And there you go. That's pretty much what you got to do. So you make an array of pointers to point to another array of pointers to point to actual data. Now, what that looks like in a very colorful fashion, which I actually did live one semester. So you can definitely check out that video if you are curious. I believe I did this one during the summer class a couple of years back. But I'm not doing this again live. Is that okay? So that's what it looks like once you get the whole thing in there. So it's pretty much the same thing I drew, just 3 times. In fact, I probably copied and pasted part of this. Yeah, looking at that. So yeah, so we got our initial pointer up here. Make this array here. Each of these is connected to these and that, okay? So if I want to access like the 42, then I have to go here, 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 and then here, okay? So, and you can see examples of the calls here. So like at the first layer, we're going to have 3 asterisks, 3 referencing, and then we're going to make a 2 asterisk array, which is representing the green one. So this here is the call for that here. To make the yellow ones, which will be in the loop, they are going to be looking like this. It will be a double pointer, and they will, in fact, if you do, because remember, with a pointer, you can make like 20,000 pointers pointing to the same spot. So if I just wanted to make a separate pointer to point to a specific array, I could do that. So I could make it something like this. And then those would also be pointer arrays, but you can see only 1 star now. So we're working our way down. Those are of size 4 because there's 4 layers, remember? 4 rows per se, layers. And then finally, at the innermost level, the ones that actually contain the data, Those are size 3 for each of the little pieces, and that's just a normal new int3. Nothing special about that, other than the fact that it's part of a bigger thing. For 4 dimensions, I would literally take this whole image and copy and paste it the many times that that last dimension would have. So if it has 4 of them, it will be 4 of these connected with an even bigger one. I am most definitely not going to be doing that one, but you can do it at home if you want. Like draw it, make an art piece, and share it with us. Leave it in the comments below, and we can all check it out. Okay, what I do want to do is I do want to code this one up for you, and keep this for reference during the tests. Don't copy and paste my code into the test. That's, I guess, cheating technically, but you can definitely use it as a reference to make your own version of the code, or even as a template, as a starting point. There's only so many ways you can do this anyways. So I encourage you to use that. In fact, I'm gonna keep going from here. I'm just gonna modify it. So let's make the 3rd dimension. It's 3. Yep, that will work. No, it won't. I gotta rename my variables probably. We'll call this one size 0. No, we'll keep it the same. So anyway, so size 1 now is going to be the innermost one, which is 3. Then the next to that is 4, and then the outermost is going to be 3. So yeah, that one. There we go. Okay, so 3, 4, 3. So for the innermost one, I am going to be adding the 3rd asterisk. Well, this is the pointer that contains the link to the whole thing, and then from there I'll call it AR3D just so it matches what I had here. So AR3D, so this is the one we gotta make, so this line of code. So I just gotta add another asterisk there and then refer to size 1. So I'm gonna go from int I to size 1, and this is where I'm gonna make the 2nd layer. So I'm making the yellow ones now. For the yellow ones, here's the call right there. So for that one, I am going to say AR3D I. This I is the same thing as if I put an asterisk there actually, so that's kind of neat. And then this one's going to be a single pointer there of size 2. Now, within that, I am going to have another for loop for the 3rd dimension that I need to add in. So for int j is equal to 0, j is less than size 2, j plus plus. Semicolon here for that. Okay, so in here it's going to be R3D IJ, and for each of those pointers I am going to allocate the gray stuff. So this is going to be the actual data. So this is just a simple int new int size 3, and that is how you do it. That's a 3-dimensional array right there. We can, of course, I still haven't shown you how to deallocate them, but I'll show you how to deallocate this one, and then you'll know how to do the other one. Let me modify my print functions to, take this into consideration. Int k is equal to 0, k is less than size 3, k plus plus. My blood sugar is getting lower and lower probably. K, IJK. Yeah, okay, that's all good, I think. And then here we need to do the exact same thing again. So for printing it, we're gonna have to, like, I don't want to do some weird fancy 3-dimensional like engine here to print out the cube. So we're just gonna print it out flat, like if different layers at a time. Yeah. That's how you normally would print a 3D array anyways. I'm not cutting any corners here. All right, so we can bring this in here. Okay, so there's my printing. IJK. Again, the printing is trivial. You should have been able to do this in the past. That's why I'm not going over it. It's just a simple for loop. I am going to add some line feet here. This line feet's there. Maybe 2 line feet here to make it easier to read. And then a line feed there. Okay, so run it. And there you go. So we got the first layer, second layer, and third layer. Okay, so those are the layers of the cube. So as you can see, I printed them split up so it looks nicer. But yeah, that's how you do it. Let's run Valgrind. Let's see all the memory leaks we have. No errors though, but we should just have memory leaks. So you can see there's no errors. It's just that we do have one definitely lost and one indirectly lost. So the definitely lost is probably the first layer, because that's from a pointer. The indirectly lost is because they were made, but there wasn't a pointer directly to them at any time. So that's why they show up under that category. The 15th and 240, the math probably adds up. You just have to remember that the pointers are probably going to be 8 bytes here, and there's an array of those. And then you got the regular stuff, which there's going to be, in this case, there's going to be 3 by 4 by 3. So that's 3 by 4 is 12, times 3 is 36, times 4, because it's 4 bytes per integer, is going to be 72 times 2, which is 144. So 144 plus, so 144 accounts for the gray stuff, plus the yellow ones. So 144 plus, there's 4, 8, 12 of the yellow ones. So 12 times 8 is going to be, oh man, 12 times 8, that's 80 plus 16. So 96. So 96 plus, crap, I forgot what the other number was. What was the number we just did? 96 plus, damn, this is blood sugar. What was the number we just added? Okay, rewind the video and figure out what the number I said was of the total. Actually, you know what? Why am I doing this in my head? Like, we have technology these days. So 3 times 4 times 3 is 36. I said, yep, times 4 is 144. Yep, plus, so 144 plus, now I forgot what the other one, 96, right? 96 plus 96, 240. So there you go. So I got it all right. So let me write that down for you instead of trying to do it in my head. So the way I got that number is we count all the stuff. So we count all the gray ones. So we know we have for the grays we basically have 12 of it. 12 of the 3 rows. So we have 12 grays. You can count them right here. 1, 2, 3, 4 times 3. So 12. So we do have 12 of these, which comes from 3 by 4 plus times 3, right? So that's getting you 36. Now we know that it's 36 integers. So each integer is 4 bytes in this system. So 36 times 4. That's where I got the which I forgot already. Jesus, man. 36 times 4. 144. And then to that, you got to add now the yellow stuff. The yellow ones are lost too. So there's 12 pointers. 12 pointers. Each of those pointers is 8 bytes. So 12 times 8 is 96. If you add 144 plus 96, that's how you're getting 240. So that's how I got that number. Okay. And then the definitely lost, which says 24 in one block, that is coming from the green stuff. So the green, there's 3 pointers. 3 times 8 is 24. So there you go. If anything, you might be asking yourself, okay, but what about the last layer, like the big one, the AR3D? That's actually not a dynamic variable. That's a static variable. That's the only thing here that's a static variable. So it's not technically lost. Like, you don't lose. Like, creating a pointer itself is not memory allocation. In fact, it's a static variable. So like doing this, there's no dynamic stuff there. That's actually a static. That's no different than this. It's just a variable type that's different, but it's no different than that. So that's why that's not included in the math of the loss. So I've proven to you that Valgrind's numbers are indeed correct. It is good to do these kind of computations by hand. because if you still lost about where this is coming from, you can kind of analyze it and see where, based on the size of it, you know. If you're like, if I see the 240 there, I'm like, oh, okay. And I have a 3-dimensional array. I'm like, that sounds about right for the 3-dimensional array. So that's probably where the leak is coming from. Because other than that, it doesn't tell you anything else about where the leak is. Like, that is one downside of Valgrind. It's just like, yo, you lost this much, but I'm not gonna tell you where. So good luck, have fun. GG easy. So yeah. So let's go ahead and do the allocation, and then we'll call it a day on that, and I will revisit the next stuff in a future video. So I can take a meal break. So we'll do the shallow versus deep copy and the constructor stuff in a future video. Okay, which I'll probably do it after I go and eat like sugar. Okay, so yeah, so to deallocate a 3D array is probably harder than the 2D array. So if I show you a 3D one, you'll be set for the 2D one. So all you gotta do is like unwind the array. So you can copy, actually, a good way to start it is like literally copy your allocation code. So like copy this, and you'll take this here, and then start writing some deletes. Okay, so go to the innermost layer. In fact, replace your new calls with delete calls. So we got 1 new call, 2 new calls, 3 new calls, right? So we're gonna take this one, which is the innermost, and we're gonna write the word delete, and then the square brackets because we're deleting an array, and then just leave what you had here, and then just get rid of the new. See, that's so simple. Like if you do it that way and organize, you won't have trouble. If you're just doing it from scratch, that's when you have trouble. For the 1 dimension here, so the one outer dimension from the innermost, it's the same thing. So like write your delete square bracket, leave the same thing you had there, and just get rid of this. And there you go. The dimension that's taken care of. Finally, for the outermost, what I want you to do for this one is, first of all, take that line of code and copy it to the bottom of the loops. So put it there, get rid of it there, and now go ahead and apply what I just did. So again, take this stuff here, remove the pointers too, and just say delete like that, and then go there like that, and I think you're good to go, just like that. Okay, if you do that, it will deallocate good, and I think you will be all good. Okay, well, the good news is that the deallocation succeeded. No problems there. The bad news is that we have an error. Invalid size of 8. Line 34. So this delete did not like the... Oh! Very right. Very right. Ladies and gentlemen, last class we spent half an hour talking about dangling pointers and how we should avoid them. And I told you, oh, you know, toy example, it's so obvious, but then it doesn't become obvious. Welcome to not so obvious, but still obvious now that you see the error, but not when I was doing it 5 seconds ago. We have a dangling pointer problem here. This line of code right here is deleting, if I bring my thing there, this line of code here is deleting the yellow one, this yellow one here, this first one. Okay, but then this inner line of code here is deleting the ones with the 42s on it. So here, let me pick the one that's color coded. So this one. So the line of code in line 32 is deleting this, or deallocating. The one in 34 is deleting these. So I'm deallocating this, but then I'm like, oh, I know I returned it, but like, yo, let me see what it actually contained in there so I can go in there and delete these. Bad, right? Bad, because you already returned this to the OS. This is like I said last video, I'm going back in the hotel to get my charger. No, like you shouldn't do that. You already gave it back. At that point, you're trespassing probably or something. Don't tell the hotel people I did that. But yeah, so what do I do to fix it? Make sure you do this delete after you've done the inner ones. So take this line of code, copy it, and paste it after the for loop, like that. Okay? I could have done cut and paste, but I want to make it obvious. I know cut and paste, so leave that in the comments. Okay, yeah. So similarly, I mean, I kind of did that for this one too, because I could have left it up here too. That would be the same problem, but I forgot to do it for the inner one. As you can see, this stuff starts to get tricky if you're not careful, and soon enough you have dangling pointers and memory leaks and all weird things. Okay, voila. All heap blocks were freed, no leaks are possible. This is what you want to see, and nothing in use, no errors. Yeah, we did it. Okay, congratulations. You did a 3D array and you deallocated it. What's that code? Like, I created you and now I'm going to take you away or something. Yeah. All right. So yeah, that's how you make three. So in today's video, we basically covered dynamic memory allocation, like actual coding it. You got to see Valgrind being used, how to read Valgrind. You got to see some of the errors, and then you got to see how to make a 2D and a 3D array. In the next video, which I'll do in a little bit, I'm going to go ahead and talk to you. I'll actually go off the same example that I just did, but I'm going to talk to you about shallow versus deep copy, and then maybe again introduce a bit of constructive destructors. So thank you all for watching, and I'll see you soon.